you like it? I don't know. Let me know. Maybe it doesn't work at all. Maybe I mess up halfway through and I have to cut this out awkwardly and you forget it and we just go back over there. Everything I'm doing is from the notes and the PowerPoints that are available to you on Canvas. Please go look at those. I spend time making them and putting them on Canvas available to you so that you can check them out at your own pace so that you can ask questions when you have them. What do you really need to know about the hydrologic cycle, what we call the water cycle? Well, you already know a lot of it, if I'm being honest. You know what solid, liquid, and gas states are called for water, ice, or water vapor. You know that it takes energy to melt and evaporate water. You know that most of the Earth's surface is salt water and that only a little bit of it's fresh water. And of that, it's frozen. Do we really need to talk about that? Probably not, so I'm not going to. It's in the notes though if you need it. So what do we really need to focus on? Well, like in weather, we need to focus on the different relationships between variables. So things like infiltration rate and runoff, and evaporation, and water retention, and porosity, and permeability. All sorts of those kind of things are what we really have to focus on. So skip all that background information. I know I do it every unit, but let's just skip it because you already know this one. Let's get into it at what factors affect evaporation rates. Well, again, most of this is obvious. You can have temperature. The warmer the temperatures, the more likely it is to be evaporated. Lower humidity. Now this might seem a little backwards to you. You're thinking, well, water in the air, we just said in weather was humidity and relative humidity, and that's right. But if you want to add more water to the air, you don't want water to already be there. You also want it to be windy, and you want to have a lot of surface area. The more the wind kind of blows it and the more surface area that's available, the more likely it is that energy can get to those water molecules and can excite them enough to make them go to a gaseous state. The last thing is, of course, we want them to be uncovered. If you have a drink in the summer and you leave it outside and you have a cap on it, it's not going anywhere. It's staying in the bottle. But if you have it open, you have a glass sitting outside on the porch or something, that water is going to get into the atmosphere and it's going to evaporate. So if you have a covering on a lake, like a frozen ice sheet or something, it's going to keep the water there. But if it's open to the atmosphere over enough time, and if it doesn't rain or anything like that, yeah, it's going to evaporate out of the lake. So how do all those things move together? Well, you know, there's evaporation and precipitation and transpiration and there's runoff, and you know all that stuff. If you don't, it's in the PowerPoints. It's all labeled there for you. But what we really care about is what really drives the water cycle, which is the same thing that drives almost everything else in earth science, which is the sun. Without the energy from the sun, without that heat energy radiating through space, we don't have the movement of the water throughout the water cycle on Earth. We just don't have it. Like we don't have photosynthesis, and we don't have any of this stuff we talked about back in the energy sources unit. We don't have any of this without the sun. So what happens then if we didn't have it? Well, we wouldn't have a planet. But we do, and we do have the sun, and we do have precipitation, so let's talk about how it interacts with the ground. There's two things that initially happen. You can either have infiltration, that's where water gets into the ground, it infiltrates the ground, or you can have runoff. And that's when, you know, on the days when it's raining a lot and you see those like streams kind of going through the ditches and all that stuff, well, it can't get into the ground, it can't infiltrate the ground, so it runs off across the surface. And there's different layers in the ground that it can go to. The first one that it gets to at the top is called the zone of aeration. And the zone of aeration kind of sounds like air because there's still air between the different particles of soil. Now, if you keep going down, eventually it's going to be completely filled. We call something that's completely filled saturated. So that means the zone of saturation has completely water. Well, that was annoying. Sorry. Anyway, so where we pick up next is porosity. And porosity is just the amount of pore spaces that's available, that's open between particles. Think pores in your skin. If you have a lot of pore space, you have a lot of open spaces for water to get into the ground. However, the thing to remember with porosity is that grain size has no effect here. It's all about shape, packing, and sorting. Shape is the shape of the particle. Is it more round? Is it more angular? Packing is how close together, how put together are they? And sorting is it all the same type of stuff, or is it a bunch of different things kind of all jumbled together? Those are the three things that affect porosity. It has nothing to do with the grain size. Now that might not make sense intuitively, but if you have all the same things, like you have three examples in your notes, A, B, and C, you would think that maybe C would have the most or the highest porosity. That's not true. They're all the same shape, they're all packed the same, and they're all sorted the same. So they all have the same porosity. So we can then bounce back to where grain size matters, which is water retention. Now, the smaller the particles, the smaller the grain sizes, so things closer to our clays and our silts are going to hold water in better. The closer they are together, because they're smaller, the more it can keep the water trapped in between them. The same thing is going to be true for capillarity. Now, if the water wants to move upwards, the less it has to jump, the better off it's going to be. If you wanted to go across a lake and you needed to, kind of skip across rocks, well, would you want to jump 5 feet or would you want to take a 5-inch step? Of course you'd want to take a 5-inch step. It's a lot easier. If water wants to go from one particle to the next, it wants to go over a smaller gap. So these smaller silts and clays, things like that, are going to have much better capillarity because it's going to give them less error or less chance of error, if you want to think of it that way. It's going to be able to move from one thing to the next much easier. So after all of that, we can start putting this together. What creates more runoff? What creates more infiltration? What creates flooding? Well, like in weather, it all just depends on all of your other factors. You can't really say it's one thing or another. Did it rain a lot? Well, maybe a little bit more rain is going to cause flooding. Has it been dry? Well, sometimes if it's not rained a lot and you get flash floods where it rains a ton, water can't get into the ground because it's so kind of clogged up already with the sediments. It won't let more in. The water can't infiltrate fast enough, so you get a bunch of runoff, which becomes a flash flood. Never try to outrun a flash flood. You can't do it. You might see some videos online of people doing it in the desert. Incredibly stupid. Do not do it. People die trying to get videos like that. Don't be an idiot. So last thing that I want to check is pollution. Now you have some checkpoints throughout your notes, and we may or may not have done them in class. It just depends on if we had time or not. You're not going to necessarily be required to know exactly how to do those, but it might not be a bad idea to understand why the answers are what they are. You already have all the answers. You can just look it up. You don't even have to figure it out on your own, but it might not be a bad idea to understand the principles behind it. The last thing we're going to talk about is pollution. So we kind of put all this stuff together and figure out how groundwater starts to move, the permeability, the porosity, the water retention, how water moves upwards, if it can infiltrate into the ground. All this stuff kind of starts to join together here with pollution. There's two different main types of pollution, overarching ideas if you want to think of it like that. There's point source and there's non-point source pollution. So point source is like the Duke power plant coal ash spill that we talked about in energy sources up near Asheville. We knew exactly where it came from. We knew it was that plant. We knew what did it. We knew what caused it. We knew what stuff it was. That's point source pollution. We can go right back to it. Non-point source pollution is when you have, like a neighborhood and a lot of people want to take care of their lawns. We have a bunch of, pesticides or herbicides or grass seed or stuff like that gets into the water system. We don't know what house it came from. It came from a lot of different places. There's no one that we can pinpoint. We can't be like, you did this, because a lot of people have done it. That's called non-point source pollution, and that happens all across the world, and it happens all across Davie County. Both of these things are important to understand, because if you figure out how pollution gets into the groundwater, we can try to figure out how to prevent it from even getting into the groundwater to begin with. But we can't be perfect. It's going to happen no matter how much we try and no matter how much we ask people to, make sure they're not dumping stuff down drains or make sure that things don't run off their lawns or farms or whatever. It's going to happen. It's just a fact of life. So we need to figure out how to mitigate it. We need to figure out how to fix it. When it gets into the groundwater, it's in the groundwater. It's going to be taken wherever the water takes it. It might get completely into the groundwater system and it gets taken a really far way away. It might be on the surface water and it gets into rivers and streams and it gets carried through that way, eventually making it into the groundwater. Regardless, that's not the only problem. When you have something, let's say a gasoline or an oil spill, it does kind of mix with the water a little bit and gets carried that way, but it also clings to the soil. And you might remember back in the energy sources when we talked about nuclear accidents and how they had to dig up that topsoil to, get the radiation out of the ground. Well, we have to do that sometimes too with, gasoline spills near a fuel station or something like that. We have to dig it up out of the ground physically. Once it's in the ground, we have to track it with a bunch of different instruments and different kind of scientific methods depending on which one it is. We use things like piezometers, or we use GPR, ground penetrating radar. We use all sorts of things like that to try to figure out where it's going. We also look at stuff like topography and what the geology of the area looks like to figure out where's the slopes going and where's the elevation. It might get stuck here and it might move there. It's a lot of work to try to figure out how to clean groundwater. So really the best bet is to just not pollute it in the first place. But it does happen. We do have to track it, and we use ISO lines for this. Now, we're not going to use isotherms or isobars or elevation contour lines or anything like that. This time it's going to be concentration of pollutants, typically in parts per million, ppm, or parts per billion, ppb. Sometimes you'll see parts per thousand, ppt. That's a lot of pollution if you're seeing it in parts per thousand. Normally it's going to be parts per million or parts per billion. So you can track it based on these ISO lines. Now, just like when we saw greater wind speeds in weather where the lines were close together, in this case, it's going to be greater sources of pollution. So whatever letter on the map happens to be close to where the lines are all put together, that's probably where the pollution is coming from. That's the source. The further away they get, the less the pollution is in the ground, the more spread out it's becoming. Now you can look at a map like the one in your notes and figure out which direction the pollution is going based on where the source probably is and where the lines are spreading further and further apart. In your case, it's at point B, that's where it came from, and it's going southwest because that's where the ISO lines are getting farther and farther apart. Do you have to memorize this map? No. Might I give you one like that on the test? Maybe. Do you need to know how to read it? Probably. Now, all of this is to say that this is a lot of stuff I'm throwing at you. You know most of it already. So my biggest advice right now that we're through pollution is figure out the main sources of pollution, figure out the different types of pollution, and then figure out all those different factors of permeability and porosity and infiltration and all of that stuff. Figure out how they relate to each other, and if you change this factor, what happens to this one, or maybe they both go up at the same time, or whatever it might be between the two different factors. Just like weather, it's not that complicated, I don't think. It's just a lot of different stuff you have to remember all at the same time. And if we're going to combine this with biosphere, which is what it sounds like we want to do, that's going to be a lot of information in one test. You can do it. I know you can do it. Don't let yourself get overwhelmed because you didn't take time to just learn it at the beginning and you tried to cram all the information at the end. We'll pick up at the next part of the notes next time, but I'd start studying those different relationships now. See ya.